Good morning. I am Chun Yi. Today, I will present the characterization of the RPLIDARA2M12. My goal is to verify the sensor's physical performance against the datasheet, specifically focusing on range, accuracy, and beam divergence. First, let's look at the hardware versus software specifications. We found critical discrepancies. For the max range, the datasheet guarantees 12 meters. But the ROS driver optimistically allows up to 16 meters. For the min range, the driver allows readings down to 0.15 meters, ignoring the datasheet's 0.20 meter limit. This creates a risk of non-linear errors in the blind zone. Crucially, regarding angular resolution, the datasheet states 0.225 degrees. However, our real-time ROS data showed a resolution of approximately 0.20 degrees. This indicates the system is adaptive. It dynamically adjusts the sampling rate based on the motor's actual rotational speed. We use this measured value, 0.20 degrees, for our subsequent calculations to ensure accuracy. Next, we evaluated accuracy. We tested the sensor against ground truth from 0.5 to 1.75 meters. Refer to the graph on slide 7. The sensor shows excellent linearity with an R-squared of nearly 1. However, we identified a systematic error. There is a consistent positive offset of plus 2.2 centimeters across all distances. This is a calibration bias that should be corrected in software. Precision remains stable at short range but degrades significantly at 1.75 meters, showing that noise increases with distance. For angular resolution, it means that the angular interval between two adjacent beams when LiDAR completes one revolution. We know the angle increment. Therefore, we can calculate how many beams there are. Now, the core of our experiment, spot size and resolution. Since we cannot measure the laser beam directly, we calculated it using the hit count method. Gesture to the diagram. Here is the principle. 1. We placed a target with a known width of 75 millimeters. 2. We counted how many laser beams, K, hit this target. 3. This is where angular resolution is vital. We multiplied the hit count, K, by the angular resolution, theta, 0.2 degrees, to get the total scanning angle. 4. Using trigonometry, specifically 2 times distance times tangent of half the angle, we calculated the total scanned width. 5. Finally, we subtracted the physical target width, 75 millimeters, from this scanned width. The remainder is the spot size. Here are the results. The spot size doubles from 6.8 millimeters at 1 meter to 13.1 millimeters at 3 meters. Most importantly, at 5 meters, detection failed. The beam spot became wider than the spacing, causing the signal to blur with the background wall. In conclusion, 1. Trust the hardware limits, 12 m. Not the software, 16 m. 2. Apply a minus 2.2 centimeters calibration offset. 3. The effective range for small obstacles is limited to 3 meters due to beam divergence. Thank you.